All right, good afternoon and welcome to ECE 164, Lecture 11 on feedback. So prior to today, we've been building up amplifiers with more and more stages. So we started off with configurations consisting of multi-stage amplifiers and then moved to differential pairs. And then last time talked about op-amps and operational transconductance amplifiers. And we're going to today harness all of that gain and start to throw feedback around these circuits. That is to put them in closed loop configurations. So the idea of negative feedback was conceived by Harold Black back in 1927. And conceptually, we can draw this as follows with a block diagram, where I have an input, I have a forward path gain that I'm going to call A, and I have a feedback that I'm going to call F that is summed at the input. Note the polarity here that this is indeed negative feedback. That is that I'm feeding back part of the output to the input with an inversion here. And so if I want to write out a equation that represents this, I would say that the gain term here, A, is equal, or the output is equal to this gain term A times the difference of Vn minus the portion of the output that I'm feeding back. So that is to say that Vout is equal to A times Vn minus F, this feedback factor, times Vout. And so I can rewrite this in terms of the closed loop gain as Vout divided by Vn is equal to A divided by 1 plus AF. Okay? And so this has some pretty powerful implications, in particular when we have large A. And so let's consider the case when this AF term is much, much greater than 1. Okay? If this AF term is much, much greater than 1, then essentially the closed loop gain, Vout divided by Vn, is approximated by just 1 over F. Okay? And so what this means is that we can build an amplifier, in this case A, with very high forward path gain, and we can set the closed loop gain of this entire structure just using the feedback network. Okay? And so the way to think about this is that if you have this large forward path gain, then we only depend on the feedback factor F. And so oftentimes we will try to shoot for this condition where you have Vout divided by Vn is approximately 1 over F, and F is very typically going to be less than 1. That is that we're feeding back part of the output back to the input. And so the example that's shown here, if you wanted a closed loop gain of 2, you need a feedback of 1/2. Okay, and so this you could implement with something like a resistive divider. Okay. Any kind of gain, feedback gain less than 1 is easy to implement and can often be implemented ratiometrically. And so that's what we're showing down here, is that if you have two resistors dividing the output voltage, we're feeding back a fraction of the output voltage that's proportional to this resistive divider. Okay. Feedback with F is equal to 1, that is unity gain feedback, is very straightforward. It's just that we're taking the output and we're summing it right back at the input. Okay. And so ultimately, what's really happening in this feedback structure is that the output, or the amplifier, is driving the output in order to minimize the error term that happens right here. Okay, and so this is why the virtual short, or the input of an op-amp, is often called a virtual short, is that we're using the high forward path gain of the amplifier to drive this essentially to the to 0. All right, so let's go through a couple of examples. If I had R1 is equal to R2, that would give me a feedback of 1/2. Okay? Let's say that I had an amplifier that had a gain of 100. Okay, so 100 is 40 dB. Plugging this into the A divided by 1 plus AF term, I've divided out the A to kind of illustrate this purpose a little bit more clearly. And so this equation for the closed loop gain is 1 divided by 1 over A plus F. And so if I had 40 dB of forward path gain, this says that the closed loop gain would be 1.96. Okay. 1.96 is not bad. But there's some applications, in particular, a lot of precision analog applications that require better than this. You know, this would be roughly a 3 and change % error. What if we needed more? So let's take an amplifier that had a gain of 60 dB. Okay, so a gain of 1,000. This error now improved. The closed loop gain is now 1.99, and so this error is 0.3% rather than 3%. So this is improving, and it's getting much better. And what this ultimately shows us is the second condition that feedback really helps with, and that's that if I have variation in the forward path gain, okay, it only changes the closed loop gain by a small fraction. Okay, and so this is really where feedback is probably the most powerful technique that we'll use in analog circuit design. It's that it's very hard to control the forward path gain of a lot of these high gain amplifiers. They depend on things like R0s, and R0 in general is a very difficult parameter to control accurately. And so in this fashion, what we're doing is we're using feedback to throw away or desensitize our amplifier to the closed loop gain. Okay, and so we're throwing away some of the open loop gain in order to achieve this desensitization. All right, so to more formally show this, we can define a term that's known as gain sensitivity. Okay, and so we're going to show that the closed loop gain, and I'm going to represent the closed loop gain for this lecture as capital A, and the open loop gain or the forward path gain of the amplifier as lowercase a. And so we'll define the closed loop gain as A divided by 1 plus AF. And what we can show is that variation in this closed loop gain, that is delta A divided by A, is simply equal to variation in the forward path gain divided by A, divided by 1 plus AF, which is equal to delta A divided by A divided by 1 plus T. Okay, and so what we're doing here is we're going to call this AF term T. And this is going to become more apparent as we go through this lecture. This quantity T is what we'll call the loop gain. Okay? And so what this quantity here is showing us is how much variation in the closed loop gain do I get for variation in the open loop gain. And what we can see very importantly is that any variation in this delta A, so that previous example, A was 60 dB, and if we had a variation of even 10% for this delta A term, it gets suppressed by this 1 plus T. Okay? This 1 plus T is essentially the loop gain of the circuit, and it fights errors in the forward path gain in this open loop amplifier. Okay? And this quantity, this 1 plus T term, in theory, we can make this arbitrarily large. Okay? And so we're going to work on ways of, or look at ways of dealing with what this T term does to other parts of the circuit in addition to the gain sensitivity. This loop gain term, it's going to appear in a lot of other calculations. It's going to show up in the bandwidth, it's going to show up in the impedance, and we'll talk a lot about this. So it's very important now to get down our notation that AF is going to be equal to T, and that our closed loop gain is going to be capital A, open loop gain, lowercase a. Okay, so now let's look at what happens when we have nonlinearity. And so what I'm doing here is I'm saying that this amplifier no longer just has a linear gain term, that is this A1X, but I've introduced a third order nonlinearity. Okay, so A3 times X cubed. And so this is giving us a cubic nonlinearity in the forward path amplifier. And what we are trying to do is we are trying to see how this nonlinearity in the amplifier affects the closed loop transfer function, or the closed loop gain of this amplifier when I have feedback around it. And so the best way to map this is to take this system and try to map it into a linear system where I take away the feedback and I just have V in getting transferred into V out with new coefficients. Okay, and so what I'm going to try to do in the next slide is calculate what B1 and what B3 are, and then we can compare them to A1 and A3. All right, so we can start by writing the output equation. So V out is going to be equal to A1 times V in minus FV out. That's the exact equation that we had earlier. In addition to that, we're also going to have this A3 coefficient, which is the third order nonlinearity coefficient here, times V in minus FV out cubed. Okay. And so now if I was to take this expression or this block diagram over here, I can write it in the following way, that V out is defined as B1 times V in plus B3 times V in cubed. And so if we do a little bit of algebra by taking the second equation and substituting it into this equation, we can map the coefficients B1 and B3 to their A1 and A3 counterparts. And what we'll find is that B1 is equal to A1 divided by 1 plus A1 plus F. Okay. This is not surprising. This is exactly what we saw previously. This is simply to say that the closed loop gain previously that we find as capital A is equal to B1, and it's equal to the open loop gain divided by 1 plus T. Okay. B3, on the other hand, is equal to A3 divided by 1 plus T to the fourth power. Okay. And so what this is showing us is that if we do have this cubic nonlinearity, loop gain, in particular this 1 plus T term, is helping to suppress the nonlinearity of the forward path amplifier. And very importantly, it's doing so for the third order nonlinearity to the fourth power. Okay, and so it's always going to be the order of the nonlinearity plus 1. And so when we have the linear term, we're going to get this 1 plus T. For the third order, we're going to get 1 plus T to the fourth. And so this is pretty powerful in the sense that now we don't have to build forward path amplifiers that are extremely linear. The feedback will help clean up some of this nonlinearity in our closed loop transfer function. All right, so now let's look at the effect of negative feedback on the bandwidth of the circuit. And so similar to the previous slides, I'm going to represent the forward path gain as A. In this case, I'm going to take into account the frequency dependence of A by calling it A of S. Okay, and A of S, we're going to show this as a DC gain term, A naught, divided by 1 minus S over P1. So this is to say that the circuit has a single pole response. Okay. And so now if I write the closed loop transfer function, it's equal to little a of s divided by 1 plus a of s times f, which is equal to a naught divided by 1 plus a naught f. This is the DC closed loop gain, okay, times 1 minus s over p1 times 1 over 1 plus t. Okay? And so effectively what this is showing us is that we have our closed loop gain, as we've derived several times now, but our pole is effectively moved out by this 1 plus t term. Okay? And so this means that we have a bandwidth that has gone up by 1 plus t, but the penalty or the price that we paid for that was we gave up gain. We gave up open loop gain where our gain was reduced by this 1 plus t term. And so if you've ever heard anybody say that the gain bandwidth product is constant, this is essentially the trade-off that we're talking about in this particular system. If I have a particular architecture for a forward path amplifier, I can change the feedback network, but essentially the gain times the bandwidth will always be constant regardless of how I manipulate this feedback network, provided that it's passive. All right, so to illustrate this graphically, what I'm showing here is a Bode plot. This upper curve is the gain or the magnitude of the response in the open loop structure. And so you'll see that the DC gain is 20 log 10 A naught. I have a pole right here at P1, and then I roll off at 20 dB per decade. The closed loop moves down to this lower curve where now my DC gain is approximately, or not approximately, it is 20 times log 10 of A naught divided by 1 plus T naught. This is the closed loop gain. And this pole has moved from P1 to 1 plus T times P1. Okay. And so here I'm just trading the gain for more bandwidth. You know, today we really take the idea that we can have a lot of gain for granted. If we go back 80 plus years and think about what was happening in 1927 when Harold Black conceived the idea of negative feedback, he had a very difficult time convincing people that this was a useful technique. This really stems from the fact that the transistors, or the devices that they had back then, were vacuum tubes. And vacuum tubes have intrinsic gains that are single digit, or sometimes in the kind of tens range. If we compare that to transistors that we have in this class or in this technology, we have intrinsic gains of 50, 100 or more. Okay? And so the idea was was foreign at the time. How do we throw away this gain when it's very hard to even make the gain? And so it turns out that even before people used negative feedback, they often actually used positive feedback. And the positive feedback was used to address this fundamental problem, that it was very hard to build amplifiers in the forward path that had high gain. And so positive feedback was something that was invented by Edward Armstrong back in 1915. Very similar conceptually with our block diagram: input, output, forward path gain of A, feedback of F. Instead of having a negative sign here, we have a positive sign, such that we're feeding back signal that happens to be in phase with the input. And so if we write the output function, the output is equal to A times the sum of V in and F V out. And so the closed loop gain is equal to A divided by 1 minus AF. Okay? And so if we take a loop gain, AF, is equal to 0.9, you can see that now the forward path gain is increased by 10x. Okay? And so this was a way at the time to harness positive feedback and achieve higher gain than you could with your open loop amplifier here with A. However, this is a difficult thing to play with, because if you think about the stability of this, it's very difficult to get these amplifiers to be stable. And so here's a picture of Edward Armstrong on a very large radio tower, and you can see that he's trying to stand up on top. And so positive feedback has stability issues, and so did Armstrong. He was quite the showman at the time. He is an inventor with very few peers. He has invented many things that we take for granted and often forget about, things like FM radio, as well as heterodyning, or ways of translating frequencies around in the spectrum. And so here's one of his very early famous patents of a mock-up of a radio. And, excuse me, not radio, his original positive feedback circuit from the patent in 1915. All right, so let's look at feedback, and let's use an amplifier in order to convey the concept here. And so what we're doing is we're going to have this circuit, very, very simple circuit. We have an op-amp, we have negative feedback. This should be a non-inverting configuration for an op-amp. Okay? And so the amplifier itself, we can write that it has a transfer function that's equal to the open loop gain times the difference in its two inputs, that is V plus minus V minus. And so I can readily map this into this type of structure that we've been talking about, where the input comes in here. I have a forward path amplifier, that's this. And then I feed back part of the output back to the non-inverting terminal. And so I'm completely mapping this kind of one-to-one to this block diagram. F in this case is equal to the portion of the signal that I'm feeding back. So it's a resistive divider. It's equal to R1 divided by R1 plus R2. The forward path gain A is equal to G of this amplifier. And so I could write the closed loop transfer function, V out divided by Vn is equal to A divided by 1 plus AF, which is equal to G, this gain term, divided by 1 plus G R1 divided by R1 plus R2. If we take the limit to G being very large in this case being relative to F, we can see that for large open loop gains, this is approximately just R1 plus R2 divided by R1. Okay, so we built a amplifier that is closed loop gain is dependent only on these two passive components outside of it. So let's take another very simple example. Let's look at the inverting configuration. Okay, and the inverting configuration, again, I have same amplifier, two resistors, but in a slightly different configuration. Okay, this is a little bit different, and what you're going to see is that it's more difficult to translate into this case. Okay? In particular, the input is a voltage, but the output, we're not feeding back a voltage. We're feeding back a current to this input. And so mapping it into this kind of structure is a little bit more difficult. It's not easy to identify what A and F are directly as we did for the previous example. It turns out that this circuit does not directly map back. We can't easily identify A and F using only voltages, and this is really due to the fact that we're feeding back this current that I described earlier. This current is a function of the difference between the input voltages here. Okay. More importantly, and I think that drives home this point, the forward path gain A here in this particular example is not G, because that wouldn't make the ratios or the units work out. The forward path gain is something else, and I'll let you work out exactly what the units are on G. Okay. Point is that while this is conceptually very simple, it's limited in its ability to work for all circuits. Okay, and so what we're going to do is build up a framework of dealing with this a little bit more generically. Okay, in order to solve this particular example that we're looking at right now, I'm going to propose a couple of solutions. The first of which is that we could simply do KCL and KVL. Okay, KCL and KVL will always work. The simplest thing here is just to do KCL at this virtual ground node. I would say that current is flowing out of R2. Current is flowing out of this resistor R1. And so I would get that the closed loop gain, V out divided by Vn, was equal to minus R2 divided by R1. This assumed that the amplifier was ideal. It was ideal in the sense that I took V minus to be equal to V plus to be 0. Okay? If this amplifier had finite gain, for example, you might ask yourself, how do I do this analysis when the gain is not infinite? We could do it a couple of ways, one of which is superposition. So we could calculate the transfer function with the feedback network turned off, and then we could calculate the transfer function with the input turned off. And so if we do this first one up top here, what we'll see is that by shorting or turning off the feedback network, that essentially means that I need to take this resistor and turn off the load. Okay, so I need to disconnect it from the output, and I have to tie it such that it loads the input in the same way. So this, looking into this amplifier, it has to be the same as the original case up here. Okay? And so I do that by grounding R2. And so now I can find the forward path transfer function. which is equal to minus R2 divided by R1 plus R2 times G. Okay? So importantly, you'll see that now this is not simply just G, this is a resistive divider at the input in order to get the forward path gain here. Next, I can turn off the input and apply a test signal to the feedback network, and this will give me my minus AF term. Again, taking the same circuit, I apply the test circuit or test stimulus to R2 while shorting R1, and I will get that minus AF is equal to minus R1 divided by R1 plus R2 times G. And so with these two terms, I can now put them together into this expression, and I can calculate that with large A, the closed loop gain is approximately equal to minus R2 divided by R1, which is what we got from the ideal amplifier case. Okay? Now, if I didn't want to make the approximation that A was very large, you can see that in these expressions, I have G, and so I could calculate the exact closed loop gain as a function of the forward path gain. The problem with this is that it takes a lot of practice to do this properly. And I say properly because you have to account for the loading on all of the nodes. It works relatively well for a op-amp because the op-amp has a low output impedance, and so it's not as sensitive to the loads. It's much more difficult when we look at things like MOSFETs where they have high output impedance, that is R0. Okay? In that case, the loading can be very, very critical to the overall transfer function of the circuit, and altering the loading can significantly change the closed loop gain. And so what we're going to build up is an alternative strategy that I think is quite elegant. It's called return ratio analysis. This is a technique where we don't have to try to find A and F individually. Instead, we focus on the larger circuit and identify the loops that will let us calculate the loop gain. This is also a technique that you will use later on in ECE 264, where we continue our journey with integrated analog circuits. All right, before we get too much into how to actually implement return ratio, I want to spend a few minutes and talk about stability of these circuits, and importantly, why T of S is very important to assess the stability, and we'll use it. So if I have a circuit that looks like this, and I'm making this very generic now in the sense that A can have a frequency response as well as F can have a frequency response. And so I can write that the closed loop transfer function A of S is equal to little a, the forward path gain of S, divided by 1 plus T of S, where T now also has a frequency dependence. The most general criteria to prove stability is what's known as the bounded input, bounded output. This applies to any type of system. And you can show that a continuous LTI system is bounded input, bounded output stable if it has all of its poles in the left half of the S-plane. And so what we'll often do is you can calculate the roots of 1 plus T of S in order to check for the stability. So we can factor this and calculate all of the position of the poles in order to look for and make sure that they're all in the left half plane. Okay? This, however, can be quite tedious and difficult to do in practice. And so many times we look at a simpler way of proxying to prove this stability. And so there's a couple of techniques, one of which is the Nyquist criteria. Nyquist essentially is to evaluate T of S on a polar plot and look at the root locus that's formed as a function of frequency. And so what you can do is that for any T of S, we can determine if it's stable at particular frequencies, okay? And so this technique is powerful in the sense that it works even if T of S, the loop gain function, is unstable. And so if you want to see some examples of this, I've listed two references here that talk a lot about control theory in particular, with relationship to oscillators in this paper, as well as a more general treatment of Nyquist. A simpler subset of Nyquist is what's called the Bode criterion. Bode only applies when T of S is itself stable. And so this is generally a useful thing and appropriate in most electronic circuits. There are a handful of small exceptions that don't work with Bode criteria. One of them happens to be oscillators that's discussed in this seminal paper by Meyer. All right, so what we're looking for in the Bode criteria is that the magnitude of the loop gain is greater than 1 when the phase crosses minus 180 degrees. Okay, and so this is one of the criteria that we're going to use. This is called the phase margin. We also need to look at the other condition of this, which is what happens when the phase, when the phase hits 0. Where is the phase, hits minus 180, where is the gain? Okay, and so that's the gain margin. So we have two metrics that we're looking at. That is where the gain is unity, we need to look at the phase, and then vice versa, where the phase is minus 180, where is the gain? Importantly, we can use a Bode plot in order to assess the stability of these circuits, which is something that we're quite familiar with looking at. All right, so here are Bode plots. On the top, I'm showing the magnitude of the loop gain. On the bottom, I'm showing the phase of the loop gain. And as I was just describing kind of clumsily, the two metrics that we'll use for the stability are the phase margin and the gain margin. We're going to call a couple of frequencies into play here. The frequency at which the loop gain crosses unity, or 0 dB unity, we're going to call that omega c. We go down and we look at the phase, and the distance between that and 180 degrees, that's what's known as the phase margin. Okay. Conversely, once the phase is at minus 180 degrees, I go up and I look at how much below unity gain I have for the magnitude, and we're going to call that the gain margin. Okay. And so the gain margin and the phase margin are the two criteria that we use in assessing the stability when looking at Bode plots. In terms of the gain margin, we typically want the gain margin to be 3 to 5. A little bit more is generally good for stability. And for phase margin, you will typically aim for 60 degrees on the lower side for continuous time circuits, and 70 or 72 degrees for discrete time circuits. Okay. All right, so let's look a little bit more at the phase margin in particular, and essentially what happens to the magnitude response when we have low phase margin. And so what I'm showing here are a couple of different closed loop gains normalized to the frequency. And so this is omega divided by the unity gain frequency of this amplifier. And so we'll see that for 90 degrees, we have very, very shallow pole. Okay. At 60 degrees, we start to see that the pole pushes out a little bit, but it rolls off or it transitions a little bit faster. Okay. And as you decrease the phase margin further, you start to get peaking. So peaking is this phenomena where we're getting gain that's increasing near the edge of the bandwidth. And so you can see that for a phase margin of 30 degrees, there's significant peaking. This is 6 dB of peaking, which is a lot of peaking. So even down here at 60 degrees, there's a little bit of peaking, but it's less than 1 dB. Up here, we have a very high Q pole, which is essentially to say that this circuit is very likely not stable. Okay? That is, it's going to want to oscillate or have very long transient settling. All right, so coming back to ways of assessing the stability. If we just want the closed loop transfer function, we could always do KCL and KVL. And that's essentially what we resorted to earlier when we encountered that inverting amplifier. That circuit was really simple. As we start to look at more complicated circuits, this can get really tedious. Worse yet, and I think this is the biggest drawback of that type of technique is that after I do all of that work, I do all of the node equations, I reduce this down to a nice closed form equation, I can't even assess the stability. I have the closed loop transfer function, but I can't prove that it's stable. Okay? And so if I really wanted to prove it's stable, now I need to go back and I need to find the roots of 1 plus t, which I probably didn't formulate my expression in that kind of structure anyway. All right, so there's a couple of ways of dealing with this. Conventionally, the way that this is taught is what's called two-port feedback analysis. This is probably something that you've seen in ECE 100. It's, I think, still taught in 264 as well. The idea is that there's 4 canonical configurations depending on what is being fed back and what the input signal is. And so shunt, series, shunt, and series feedback are all different configurations of two-port network. You still have to identify A and F and appropriately load the circuit in order to find the closed loop transfer function. There's lots of really nice, simple examples that map perfectly into this, but there's a whole bunch of circuits that don't, right? And so to give you a couple of examples of circuits that do not map into this, things like bias circuits. So take, for example, our constant GM. Our constant GM, if you recall, we have the 2 transistors on the bottom that are generating this delta VGS, but then we're feeding back a current based on the output of that second transistor back into the input, and we did this in order to remove the supply dependence of that circuit. Another example is an oscillator. It only has 1 port, it has an output port, it doesn't have 2 ports. Okay? And so what we're going to discuss in just a second is a much more generic framework that works for all of these circuits regardless of whether or not they have 2 ports. All right, so to set us up for this, let's look at this example that I'm showing here. Resistive input, resistive feedback. Instead of showing this with an op-amp, I'm now trying to implement this as an integrated circuit. And so I have an NMOS transistor here. I have a current mirror that I'm using to bias this transistor. Okay? And so my amplifier here looks something like this. Okay, and so what I want to do is I want to map this to my AC equivalent circuit. Okay, and so my AC equivalent circuit, I'm going to simply say that this transistor has a transconductance, GM. Okay, I'm going to neglect channel length modulation for a second so I don't have RON and ROP. Okay? And I'm going to include CGS just to show you what impact this has on the circuit. All right, so I can write that the closed loop gain is equal to V out divided by V in, which is equal to A of S divided by 1 plus A of S times F of S. The problem here is that I can't easily pick out A of S and F of S. So similar to when we were doing this with an op-amp, it's not easy for me, or anyone really, to say what A of S is and F of S is, given in particular this capacitor. Okay, so this capacitor is presenting a problem at the input because it's not letting me decouple these 2 terms, these A of S and F of S. So let's resort to the simplest thing. Let's go back and do exact KCL, KVL, and then we'll build this up and analyze this circuit a slightly different way. All right, so using this expression, we can write out 2 equations. I can do KCL at Vx, and so I can say that Vx, Vn minus Vx divided by R1 plus V out divided by Vx divided by R2 is equal to 0. That's this first expression. And then I can write that Vx minus V out divided by R2, that's the current that flows through here, has to be equal to the current that flows through this transconductor here, GMVX. For simplicity right now, I'm neglecting this capacitor. I'll add it back in just a second to show you what happens, but it would be fairly easy to add an additional term to this first expression if we wanted to account for it right now. All right, so what I get is that Vx is equal to V out divided by 1 minus GMR2. And so plugging that back into that expression, this expression, and reordering it, I will get that V out divided by Vn is equal to 1 minus GMR2 divided by 1 plus GMR1. Okay. If I factor out this R2 over R1, okay, I will get that there's the second term here, which is equal to 1 minus 1 over GM2 R2 divided by 1 plus 1 over GM R1. Okay. This is the closed loop gain of this amplifier, and this term over here, we're going to see in just a second, this is the loop gain. So the loop gain is equal to GM times R, and if we have high loop gain, we can show that this particular portion of the equation will cancel out, okay? All right, so if we did have this GMR much greater than 1, this would exactly agree with the op-amp solution that we were just describing. All right, so now let's look at this alternate feedback model that I'll describe here, and then we will go back and analyze that circuit that we just talked about using this alternative structure. Okay. So this is what's known as the return ratio model. And one of the things that the return ratio model tries to capture is the bidirectional nature of feedback. So feedback we often think of as just taking the output, going back to the input. It turns out that we've seen many examples of feedback networks already that are not unilateral. So unilateral means output is only coming one direction, whereas in the unidirectional or bidirectional case, we have the signal possibly feeding forward to the output. Okay? And so we're going to capture all of these terms with this model. And so D will be our feed forward, A infinity will be our feedback, and then we have our term here that's R times A infinity. All right, so if I want to write an expression that describes this, I'm going to do exactly like we did previously. I'll start with the signal that I'm going to have right here. Okay, so the signal that I have right here is going to be S in minus S out divided by A infinity. Okay, that's going to be multiplied by the return ratio times A infinity. Okay, and that will appear at the output in addition to this feed forward path, which is equal to D times S in. Okay. And so if I solve for the closed loop gain, okay, that is S out divided by S in, I will get that the closed loop gain is equal to A infinity times R divided by 1 plus R plus D divided by 1 plus R. Okay. It turns out that this R is really just another way of saying T, which is the loop gain of this circuit. Okay. So why do I want to use this, this particular type of feedback model? There's a couple of reasons that I think are pretty valuable and powerful. Number one, all of the terms are computable and measurable with SPICE. What I mean by that is I can figure out A infinity with an AC simulation in SPICE. I can calculate D with an AC simulation in SPICE. I can calculate this R term here with a simulation in SPICE. And so all of this lets me do simulations in SPICE to verify my hand calculations for the closed loop gain. More importantly is that I make no assumptions when I'm analyzing the circuit to try to figure out idealized portions of the circuit, i.e. this only contributes to F or this only contributes to A. I don't have to worry about the loading. This technique fits in and solves a lot of the problems that we saw with the previous approaches. All right, so as I said, this return ratio analysis, we don't try to identify the feed forward gain. We don't try to identify the feedback network separately. We simply try to find the gain around this feedback loop. And so this is what we're going to call the loop gain, loop transmission, return ratio, T, A of F. These are all the same thing. They mean the loop gain. Once I have this loop gain, this is important because now I can determine the closed loop gain, I can determine the stability, and more importantly, we can also determine the impedances. So feedback will affect the input and output impedance of the circuit. And if we have the loop gain, we can see how the impedances change. So the impedance, depending on the type of feedback that we have, it will always go up or down by 1 plus t. All right, so we can also apply this technique to arbitrary feedback circuits, i.e. those oscillators that I was talking about, or bias circuits. However, in order to get our feet wet, we're going to start with the simple circuit that we've been analyzing on the previous slide. All right, so the cookbook procedure for return ratio analysis is to first set all of the independent sources to 0. This is exactly the same thing we do anytime we're doing a small signal analysis of a circuit. Then we're going to identify a controlled source in the feedback loop that we want to analyze, and we're going to disconnect this. Almost always you'll want to do this with something like a voltage-controlled voltage source or a voltage-controlled current source. It turns out that transistors naturally have this transconductor element, GM, that we can always use to break this. Then we're going to inject a test signal, okay, of the same type as the one we removed. So if we removed a voltage-controlled current source, we would inject a current. If we removed a voltage-controlled voltage source, we would inject a voltage. Then we're going to find the signal that returns back from this loop, and I'm going to call this SR. The return ratio, RR or T, is then equal to minus SR divided by ST. If we broke the loop that we wanted to analyze, then we can also use this in order to assess the stability of the circuit. Okay. All right, so let's go back to this example, and let's now calculate the return ratio. So again, we're going to start by ignoring the effect of CGS. We can add it back in with pretty much relative ease in just a second. All right, so we're going to first disconnect this transconductor. So I'm turning off the GM by shorting it here, and I'm going to label this current IR. This is my return current. Since I've taken this out, I'm now going to inject a current IT. This current here matches the same type of source that I cut. Okay. All right, so now we can calculate IR divided by IT. And so I would start by saying this current IT that I'm injecting, it's flowing through R2, it's flowing through R1. This is the only path. And so this voltage here, VGS, is going to be equal to minus IT times R1. Okay. Once I know VGS, I can calculate this return current IR. IR is simply GM times VGS, which is minus GM times R1 times IT. And so my return ratio is going to be equal to minus IR divided by IT, which is GM times R1. Okay. So this is the loop gain of this particular circuit, is GM times R1. And we saw this previously when we did the nodal analysis, that this popped up a couple of times in the expression. All right, so next we're going to calculate A infinity. And A infinity is defined as the transfer function, the closed loop transfer function, when the gain element becomes infinite. Okay? And so essentially what that's saying is that this transconductor is now infinitely strong. Okay? And so intuitively, the way to think about this is that with our op-amp circuit, we assumed infinite gain. That meant that V plus went to V minus. Okay, it servoed out that error at the input. It will do the exact same thing in this particular circuit where this input node here, VGS, is going to have to be 0. Okay, and so what that means is that if I was to do KCL at this node, all of the current that flows through here would flow through R2 to the output. Okay, and so writing this out mathematically, this is Vn divided by R1 is equal to minus V out divided by R2, or V out divided by V in is equal to minus R2 divided by R1. Next, this D term, this is defined as the transfer function when the gain element becomes 0. Okay, so here it was infinite for A infinity, now it's going to be 0. Okay, so in this case, this GM generator is going to be turned off. It's like I took GM and no current will flow through this. Okay? If I have no current flowing through this, then essentially there's no current that flows anywhere in this path. Okay? And so that means that V in is simply equal to V out. Okay? There's unity gain in this because there's no current that's flowing through this transconductor. All right, with that, we can now put together our closed loop transfer function. So this is the return ratio divided by 1 plus the return ratio times A infinity plus D divided by 1 plus the return ratio. The return ratio of the loop gain we said was GM times R1. A infinity was minus R2 divided by R1, and D was equal to 1. And so this gives us the closed loop transfer function that A is equal to GM times R1 divided by 1 plus GM R1 times minus R2 divided by R1 plus 1 over GM R1. Okay? And more importantly, we also now have this loop gain term that we can use to calculate and assess the stability in addition to the closed loop transfer function. All right, so let me show you a couple of examples of feedback. Oftentimes feedback is very obvious in circuits. That is that we're taking the output and we're feeding a portion directly back to the input. In this case, R2 is an example of feedback. We can do this with capacitors as well. In this case, CF is feeding back part of the output to the input. In our differential amplifier, we saw an example with a technique known as neutralization, where we're trying to cancel the effect of CGD. And we did that by taking the input and adding a capacitor to the inverting portion of the output. So the negative version over here, so these are cross-coupled capacitors. Okay. Again, input, output, we're coupling capacitors between the input and output or resistors in all of these cases. There's also cases where feedback is not so obvious. This is a good example here with our two-stage amplifier. So if I look at the input and I look at the output, across this two-stage amplifier, there's no feedback between the two stages. Okay? There is, however, feedback across the second stage. So the second stage of this amplifier has CC, which we use in order to create a dominant pole. However, we see that it also creates a 0 as a result of that. Okay? We've also seen this circuit several times where we have a common source amplifier, but we have some source degeneration down here, R1. This is another form of feedback. In this case, it's not sensing the output voltage, but it's sensing the output current. Okay? And it's taking this output current and reflecting it to a voltage that is then fed back to the input. Okay? It's not directly fed back to VI, but it's fed back to the source terminal, which is coupled to the input. And so this is a form of, another form of feedback, even though it doesn't touch either the output or the input terminal of the circuit. All right, so I want to spend a few minutes and I want to talk about this notion of common mode feedback. So a lot of the feedback that we've talked about to date has been feedback around a differential amplifier. But I did mention back when we were talking about OTAs that if we did want differential outputs, we need a way of setting this DC voltage at the output node. Okay? And importantly, this occurs because I have essentially what looks like two current sources. I have this PMOS current source and I have this NMOS current source with a very ill-defined voltage in the middle. Okay? It's only really after I consider second order effects of the output impedance in the DC biasing calculation that we can figure out what this Vout node is. Okay? And so this is where this type of feedback can also be used, but for what's called common mode feedback. And so in common mode feedback, what we're going to do is we're going to sense the output voltage, the output common mode voltage, and we're going to compare it with a desired output common mode voltage, and then feed back part of this to the input. Okay, so in this case, it's using the tail current source down here. We've split it up into two tail current sources, and we're using this one in order to set the output common mode voltage. All right, so there's a couple of ways of sensing the common mode voltage. I'll start with those, and then we'll move on to how we would actually use this to feedback and then correct the output common mode. So let's take a differential amplifier. In this case, both of the inputs would be tied to a common mode voltage VICM. Okay? And what we're doing here is we're taking the output from VOM and VOP, and I've added two resistors, R1 and R2. Okay? And so if we write KCL, we can find that the output common mode voltage is equal to VOP times R1 plus VOM times R2 divided by R1 plus R2. And if we have R1 is equal to R2, that is that these two resistors are the same, then we will get that the output common mode voltage is simply the average of VOP and VOM. And so we're using these two resistors to find the midpoint, or the average, of the two outputs. Now, importantly, if we think about the differential mode gain of this amplifier, we would need to make these two resistors large, not to load the amplifier. Okay? And the easiest way to think about that is if you were to look at the impedance looking up into the circuit and the impedance looking down into the circuit, these two, the structure, or the simplified structure here of an amplifier, would have very high output impedance. Okay? Essentially on the order of, it's going to be approximately GM R out squared. Okay? And so if I don't want to ruin the gain of this amplifier, where the gain is going to be equal to, the DC gain is going to be equal to GM times R out, okay? I need to make R1 and R2 large, okay? Because R1 and R2 essentially fall in parallel with this expression. Okay, and so you can see that if R isn't even as large as the output impedance, it starts to attenuate. Okay? Unfortunately, with large resistors also come large parasitics. Okay, and so I'm going to end up with capacitance at this node, capacitance at this node, and also capacitance at this node. Okay, the output capacitance here, this is bad for the differential mode bandwidth. The capacitance here is bad for the common mode bandwidth. Okay? And so this tends to degrade the frequency response of both the common mode and the differential mode paths. Okay, so one way of fixing this is to not load the amplifier directly, but essentially to add a unity gain buffer. And so we're going to add this unity gain buffer by adding a source follower. Okay? And so I'll take the output with a source follower and then connect it to these resistors. And so in a sense, what I'm doing is I'm hiding these, the loading effect of these resistors from the main amplifier. And so this is good because it reduces my constraint of having R1 and R2 be very large in order to sense the output common mode voltage. The downside is that now I need to account for the swing. So this node, the swing of this node could be limited by M8 or M7 in this case, in the sense that I can't swing too high or too low because I need to keep this unity gain buffer in saturation. I also suffer a penalty in terms of the power. since I've added 2 additional branches on each side of this in order to sense the output common mode voltage. Another technique is using transistors themselves, but putting them in triode. Okay, and so in this example here, M7 and M8 are transistors with very high overdrive voltage. You can imagine that this node is approximately VDD over 2, and so VGS for M7 and M8 is very large. It's also VDD over 2, and so they have very high overdrive voltage. Okay? Essentially what we're doing is we're using M7 and M8 in triode in order to calculate or average the voltage here at P. Okay? The biasing, I should mention, in this particular circuit is not shown. I'll show you a little example later on where I do put this into an actual amplifier and how you would use this. So this circuit is nice in the sense that it doesn't load the amplifier with a resistive load. We do introduce a small capacitive load from M7 and M8, the gate capacitance here. However, the downside about this approach is that it's very nonlinear. It's nonlinear in the sense that RDS in triode is fairly nonlinear itself, and it's very voltage dependent, which if you have a lot of voltage swing here can cause this triode common mode feedback to also be nonlinear. All right, so one more way of sensing the output is what's known as a differential difference amplifier, or a DDA structure. The DDA structure is shown up here. Essentially, we have 2 differential pairs where one side is connected to VOM, the other to VOP, and then the middle nodes I'm going to connect to my desired common mode voltage. Okay? And if I have a fixed tail current on both sides of this, what's happening is that we're getting current steering at this node depending on how this relates to VOP and VOM. And so you can kind of think of this like 2 teeter-totters. Okay? Where we're steering this current either to VDD, we're just pulling it out, or we're going to sum these 2 currents into this variable here, ICM, because I've tied the outputs of both sides of this together. Okay, and so what this circuit does is ICM is proportional to VOP plus VOM, and so this lets me sense the common mode current here. I generate a common mode current that's proportional to VOP plus VOM. So this is a way of generating a current that I can then feed back into the amplifier by mirroring this and then putting this into like a tail current or an active load in the amplifier. This is a good structure in a lot of ways, has really good linearity compared to the previous case. Still has the downside that if I have very large output swing, it can be problematic in the structure because we can end up with full current steering of the tail current, essentially saturating this. So we need to keep M1 and M3 in saturation given the output swing of the amplifier. Okay, so how do I actually integrate this back into the amplifier itself? We know how to sense it. Here's a couple of examples of amplifiers that have common mode feedback built in. So the simplest structure, this is akin to us just putting a resistor up here. We're using a diode connected transistor M3 and M4 in this case. The downside about this particular structure is that the gain, the open loop gain, is equal to GM times R, where this R is equal to the impedance that I see looking into M3, which is 1 over GM. And so this is a gain of GM1 divided by GM3. Okay, so we've seen this circuit many times. We say that the circuit is ratiometric in the sense that depending on how I ratio the size of these 2 transistors, I can get gain. Okay, but I can't get a lot of gain. 20 dB is pretty difficult with this structure, and certainly not much more than that. Alternatively, I can decouple this problem a little bit by adding this resistor here, RF. Okay, and so RF, what this does is that this particular structure in the differential mode, this node is a AC short, and so the gain of this structure is equal to GM1 times ROP times RON in parallel with RF. Sorry, I ran out of room. However, for the common mode, we have no current that's going to cross over this boundary. And so the common mode gain looks exactly like this structure over here. Okay, and so this is a nice way of decoupling the common mode and the differential mode gain without having to have the low impedance like we did here. All right, so let's look at incorporating the triode common mode feedback. Again, I have the main amplifier here. I'm taking the output nodes VOP and VOM, and now I'm using them as part of the tail current source. Okay, and so the tail current source down here, I'm essentially sensing and also using them as part of the common mode feedback. And so these two transistors, or this particular structure, you need to be very careful about how you size M7 and M8 to do the sensing as well as the common mode feedback. And they tend to add quite a bit of capacitance at both this node and at the tail node here due to how we size them given their very large overdrive voltage. They're also sensitive to PVT given the strong relationship between the sizing of M7 and M8 and the output common mode voltage. And so usually when you do this, you'll do some calculations and then you'll sweep the size of M7 and M8 to kind of dial it into the right place. All right, so here's a little bit more classical structure. So we're taking a common mode, or excuse me, a folded cascode amplifier. We are sensing the output common mode voltage with R1 and R2, and we're feeding this back with this amplifier driving the common mode voltage. And so this amplifier is essentially trying to drive this node here to the output desired common mode voltage. Okay. And it's doing so by manipulating the current through M3 and M4. We also could have done this with ISS and with the PMOS load. So instead of feeding back this voltage here, we could have connected it and fed back the voltage here, or alternatively, we could have done this node here. Okay. I will say that typically, given a choice, I will almost always do this node. Okay. This node in particular, because the current that flows through these transistors is the sum of the current on this side and the sum of the current on this side. And using the common mode feedback to bias these transistors actually simplifies the overall biasing of this amplifier, since then every transistor in this, the load stage here, all has the same current, and it's very easy to bias this tail current. These two transistors in a folded cascode are the trickier two transistors to bias, just because they contain the sum of these two currents, especially if they're not equal. You do have to be careful with where you feedback the circuit, and in particular, you have to watch for startup issues. So in this particular example, all of the current is being pulled through M3 and M4. Oftentimes what you'll see is like what I've showed on the previous slide, which is where we will break up the tail current and split it into two transistors, feeding back part into the tail and part into the we'll have a fixed amount of current, and that mitigates kind of some of these startup issues. All right, so to quickly summarize today's lecture, we showed that feedback is a very powerful technique. In particular, it helps to reduce the gain sensitivity and the nonlinearity of the forward path amplifier. We then looked at techniques to assess the stability of circuits, and one of which we found was very promising was the return ratio methodology that let us calculate T of S for arbitrary circuits. And then lastly, we ended up by talking about common mode feedback sensing and feedback strategies in order to set the output common mode voltage of these amplifiers. Thanks.